Good morning, everyone. Welcome to the session on statistical physics for the BSc Physics students. Today, in this session, we are going to solve some numerical problems on Fermi Dirac statistics. Before going to solve the numerical problems on Fermi Dirac statistics, let me give you some useful tips to properly solve the physics problems. If you follow these tips, it may help you to easily solve the physics problems. They are: read the problem twice. Even the problems looks very easy for you, you must read the problem twice. Then understand the problem correctly. Note the given values are some standard universal constants which are required for the given problem. Convert all the physical quantities into the same system of units, let's say CGS or MKS system of units. Put a question mark for the physical quantity which you are going to calculate or required to find. Write the most appropriate and relevant formula. Substitute the values and simplify the problem. Don't forget to write the answer along with proper unit. Now let's see the numerical problems on Fermi-Dirac statistics. Here once again I am recalling the formula which we have already learnt and which are required for today's session. For the particles obey Fermi-Dirac statistics, the number of distinguishable arrangements for Ni particles in Gi cells is given by Wi is equal to Gi factorial divided by Ni factorial into Gi minus Ni factorial. Here Ni is the number of particles in the ith energy levels, Gi is the number of cells in Gi energy level. The total number of eigenstates for the whole system or the thermodynamic probability is given by Wi is equal to the capital pi into Gi factorial divided by Ni factorial into Gi minus Ni factorial, where this capital pi denotes multiplication of terms for various values of I is equal to 1 to k. Now the first problem is like this. A system consists of 5 particles arranged in 2 compartments. The first compartment is divided into 6 cells and the second into 8 cells. The cells are of equal size. Calculate the number of microstates in the macrostate 2, 3 if the particles obey Fermi-Dirac statistics. Please follow the tips which I have given earlier to solve the problem. Given the total number of particles n is equal to 5 and the compartments k is equal to 2, G1 is equal to 6, G2 is equal to 8, what they are asking is to find W of 2, 3. As the particles obey FD statistics, the number of microstates in the macrostate N1, N2, N3, etc. Nk or the thermodynamic probability of the macrostate is given by W of N1, N2, N3, etc. Nk is equal to pi of Gi factorial divided by Ni factorial into Gi minus Ni factorial, where pi denotes multiplication of terms for various values of I is equal to 1 to k. Here for k is equal to 2, the formula can be written as W of N1, N2 is equal to G1 factorial divided by N1 factorial into G1 minus N1 factorial into G2 factorial divided by N2 factorial into G2 minus N2 factorial. Now let me substitute G1 is equal to 6 and G2 is equal to 8. We can see W of 2 comma 3 is equal to 6 factorial divided by 2 factorial into 6 minus 2 factorial into 8 factorial divided by 3 factorial into 8 minus 3 factorial. Let's simplify this. Then we will get 6 factorial divided by 2 factorial into 4 factorial. This 6 minus 2 gives you 4 factorial into 8 factorial divided by 3 factorial into 5 factorial. Therefore, we will simplify this as 6 into 5 into 4 factorial. That 4 factorial cancels with the denominator here 4 factorial. We are left with 2 into 1. Similarly, in this side 8 factorial divided by 3 into 5 factorial we write as 8 into 7 into 6 whole divided by 3 into 2 into 1. Therefore, we will get 15 into 56. If we multiply these two, we will get 840. Therefore, the number of microstates in the macrostate 2, 3 are the thermodynamic probability of the macrostate 2, 3 in the given problem is 840. Let's move on to the second problem. A system has 7 particles arranged in 2 compartments. The first compartment has 8 cells and the second has 10 cells. All cells are of equal size. Calculate the number of microstates in the macrostate 3, 4 when the particles obey Fermi-Dirac statistics. The solution for this problem is given there are 7 particles and 2 compartments. Therefore, K is equal to 2. And the first compartment is divided into 8 cells. Therefore, G1 is equal to 8. And the second compartment is divided into 10 cells. Therefore, G2 is equal to 10. What they are asking is to find W of 3, 4. Similarly, as we have done in the previous problem, the number of particles as the particles obey Fermi-Dirac statistics, the number of microstates in the macrostates n1, n2, n3, etc. nk is given by W of n1, n2, n3, etc. nk is equal to pi of gi factorial divided by ni factorial into gi minus ni factorial, where pi denotes the multiplication of the terms for various values from I is equal to 1 to given k is equal to 2, therefore W of n1 n2 is equal to g1 factorial divided by n1 factorial into g1 minus n1 factorial into g2 factorial divided by n2 factorial into g2 minus n2 factorial. Here g1 is equal to 8 and g2 is equal to 10. Then substitute these values into this formula. We have W of 3, 4 is equal to 8 factorial divided by 3 factorial into 8 minus 3 factorial into 10 factorial divided by 4 factorial into 10 minus 4 factorial. Here we have the simplification like this: 8 factorial divided by 3 factorial into 5 factorial, because 8 minus 3 is equal to 5, into 10 factorial divided by 4 factorial into 6 factorial, because 10 minus 4 is equal to 6, is equal to 8 into 7 into 6 into 5 factorial. This 5 factorial cancels with the denominator 5 factorial and we are left with this only, into 10 factorial I written as 10 into 9 into 8 into 7 into 6 factorial. That 6 factorial cancels with the denominator 6 factorial. Therefore, we are left with this one. Then I return this 4 factorial as 4 into 3 into 2 into 1. If we simplify this, we will get 56 into 210. Therefore, is equal to 11760. Therefore, the number of microstates in the macrostate 3, 4 are the thermodynamic probability of the macro state 3, 4 in the given problem is 11,760. Let's see one more problem. Calculate the number of ways of arranging 8 fermions in 12 phase space cells. Given Ni is equal to 8, Gi is equal to 12, Wi is equal to what? These particles are identical, indistinguishable, having half integral spin. They obey Fermi-Dirac statistics, according to which only one particle can occupy one cell. The number of distinguishable arrangements of Ni particles in Gi cells is Gi factorial divided by Ni factorial into Gi minus Ni factorial. Accordingly, different ways of Accordingly, different ways of distribution of Ni is equal to 8 particles in Gi is equal to 12 cells are given by Gi factorial divided by Ni factorial into Gi minus Ni factorial, that is equal to 12 factorial divided by 8 factorial into 12 minus 8 factorial is equal to 12 factorial divided by 8 factorial into 12 minus 8 is 4, therefore it is 4 factorial. That is equal to 12 into 11 into 10 into 9 into 8 factorial. This 8 factorial cancels with the denominator 8 factorial. We are left with 11,880 divided by 24, that is equal to 495. Therefore, the number of ways of arranging 8 fermions in 12 phase cells. Therefore, the number of ways of arranging 8 fermions in 12 phase space cells are 495. Practice more problems for better understanding. I hope you have understand how to solve the physics problems easily, and specifically in this session problems on Fermi-Dirac statistics. Thank you for watching the video. Have a nice day.